Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in lecture number 6, 7, I think so. In this lecture, basically, as I have started my design, basically analysis of composite section. So this is basically the continuation of same topic. Okay, I want to do some other examples, because after this we have to start basically design of composite section. That is a little bit complicated and tricky part. So for that purpose, if your analysis is strong, then the design is easy for you even. For example, if you are weak in analysis, basically then design would be difficult for you. So for that, due to that reason, I want to practice some other numericals on analysis of composite section. Basically, before starting the analysis of this section, as we have did in lecture number 5, I think so, or 6, we did this example. Okay, and in this example, basically here I have to clear you some a point. Basically, when we have basically, you see, there we basically use the rectangular beam analysis, you can say, or you can say we basically we start directly that this plastic neutral axis lies within the concrete. How would you know, basically? Okay, for that purpose I already explained this point here. Okay, that if your Fy is less than Cc, that is the strength of the concrete, or you can say force of the concrete, or compression of the concrete, then this decide that your steel control the design and the P in A lies within the concrete. So this point is very important. And you see here, when we calculate basically our T and Cc, so we see our Cc comes out to be 735, our T is 735 and Cc is 2040 kips. So that's why our as T or as Fy is more than Cc. So this means that your plastic neutral axis lies within the concrete section. Okay, so if it is less than basically this one, or this one, basically sorry, this one is greater than this one, then the plastic neutral axis will be in this region, or in, you can say, in web portion. So let us start in another example. This example I select from the Sam's UE book. Here, same like example like we did last time. Okay, compute the available strength of the composite beam of example 9.1. basically assume that sufficient stud anchors are provided for full composite action. Okay, so this thing is very important. There is no partial composite action, full composite section. Let's determine the compressive force as we did in the previous example. So you need to find out Cc and ASFy. Once you find out these two values, you see your Fy is 50, which is given in example number 9.1. If I show you example number 9.1 here we have example number 9.1. This one. You see, a composite beam consists of this section and an A992. Remember, A992 steel has a yield stress equals to 50 kSi. With a 5-inch thick, 87-inch is the effective width of the, that is BE or B. And the strength of the concrete 4 kSi. And determine the maximum stresses, we don't have anything with the other data, but the important thing is that we know about FC prime, we know about Fy, and basically A is section is basically, you see, 16 roundabout section. So go to the table and search that section and find out the AH, which is 10.6, as we did in previous example. So please use those guidelines and find out this 10.6. Clear? You got this one. Now you find Cc. Okay, FC prime is 4, AC is basically nothing. This is BE, that is 87 given, and this is the thickness of slab, it is given, and you find out 1479. So here the same case is in our previous example. A is Fy is more than this one, so our P in A, plastic neutral axis, lies within the concrete, and that's why we select the lower value, that will be our C value, and this is the force value. This means that the full depth of the slab is not needed to develop the required compression force. The stress distribution shown in figure, this is your required figure, and you see plastic neutral axis lies within the concrete section. You have to determine your Y distance, that is lever arm. Okay, how we find this distance Y? Simple is dy 2 plus you need to add the thickness of the concrete. Okay, this is a simple calculation. Okay, remember, this is not tricky. You have to find out basically Y. So that is, you can say, this is your thickness T, and this is your half thickness. Clear? This is your half thickness. If you add these two values and then you subtract that small a over 2, the small a over 2, you will reach to basically to find this Y. Okay, so this is a kind of approach you need to understand. Clear? Now same I did this in previous example, so please watch lecture number 5, I think so. In that lecture you will see how we can do this calculation. Clear? So you see the rest of calculation. C is basically, they have find out A, and A is nothing, that is the C which you find from the previous one, the smallest value divided by that values, just like you do in concrete. And now C, that is the resultant force of the concrete, lies at a distance of a over 2. You need to find out the lever arm. I explained this in my previous lecture, so watch this, and the resultant moment capacity will be Cy or Ty. Okay, so the minimum value, that is 530, you just need to multiply with lever arm, you find your strength, multiply this with a reduction factor, that is 0.90, you got the value 479 feet. Clear? The next topic is basically shore versus unshore construction. This is very important topic because this will help you in analysis and design of composite section. This is basically from here our basic composite section topic begins. What is shore and what is unshore? You already know about this. I want to show you some videos, some pictures, then you will understand what is shore and what is unshore concrete, and then we come to this topic and we will do an example. Clear? So let us watch this video, as we already watched this video in lecture number 5. Okay, so student, basically one thing you must keep in mind, that in this video basically you see here basically in the top floor, you see here the top floor. Basically, if for example, if concreting is done over that floor and you don't provide any shoring to this, let me show you the shoring. Okay, then we come back to this topic. Clear? Let me show you this, what is shoring. Clear? Let us, you see, this is a steel formwork which is provided to the slab. These are steel columns. Clear? And you see these shoring. Clear? Or you can say these vertical supports. This is called formwork. In local language, this is called shuttering. So this shuttering basically is formwork is provided initially to the slab. Okay. So if this kind of formwork is provided, if this kind of shoring is basically provided, we say that this is shore concrete. Clear? How basically it affects the design of composite section? the main purpose or the advantage of such shoring concrete is that it initially provides basically lateral support, or you can say it avoid the beams basically from, that is girded from lateral torsional buckling. So one advantage. The other advantage is that the beam have nothing to support. Its own weight is also coming on the shoring, and that's why at initial stage basically there is no loading on the concrete. Once the concrete is done and the concrete get its strength basically, or you can say the concrete is covered. So after that basically the composite action begins and the slab and beam behaves like a monolithic structure. So there is advantage, okay, there is a great advantage because the total load is then taken by the composite action. If we don't provide this shoring, okay, so that is called unshored construction. Okay, in that case the beams, you can say the girders or the beams are responsible for taking its own weight, the concrete weight at initial stage up to 28 days, you can say, and the construction loads, that is the machinery load, the people load, which is basically you see in this video that these machinery load, this concrete load, all these corrugated sheet load is now taken by what? By these steel girders, because no shoring is provided. In this concreting process there is also no shoring is provided. So that's why we call them basically unshored construction. Clear? So if I want to show you other pictures, let me show you. There is great advantage of shored concrete. Okay, great advantage. See, we have different construction, shored construction here. Okay, we have one picture that is very important to show you. Okay, where it is, you see almost we provide these shoring to concrete structures, because a concrete have no capability to, because in initial stage, to support its own weight. So you see all these shorings. Okay, and for example in this picture you see, if you provide such kind of vertical supports to the beams initially before the hardening of concrete, so such kind of construction is basically called shoring concrete. Clear? And if you don't provide these form works, clear? If you don't provide these form works, then it is called basically unshored concrete. So this is the difference. This is very important. Okay. Now coming back to this video, you see, if you provide such kind of shoring to the in this roofing system, okay, such kind of vertical supports, basically initially vertical supports, and then horizontal, you can say horizontal members, and then plyboards and hardboard which is provided. Okay, and basically these lateral bracing which we initially provide in shape of formwork. So it provides a lateral stability to these beams, and it increases its strength at initial stage. And basically the beam have nothing to support in initial 28 days. Once we remove these shoring basically, then the combined action, or you can say the composite action of this concrete and the beam taking the whole load. If we don't provide these kind of initial support to this flooring system at initial stage, then the beams are responsible, as I already mentioned. Okay, so let us watch the rest of the video. Okay, this is the way how it composite section basically in case of basically steel form work, steel concrete basically done, and how the construction, steel construction slab basically constructed in case of composite section. Okay, this is concrete pump which basically bring the concrete from lower portion to the top portion. Clear? Here you see, look, in this video you can clearly see here, look here, I will play it in a slow motion, so I don't have that option here, but you see the space right here, okay? You see the space right here, that in here you see the girder or the beam which is right here is unsupported. So this means, this suggests, this shows that the concrete in this process is unshored concrete, unsupported concrete, okay? Because no shoring. You watch this area. Look, this is open, means the beam is not supported by any other additional support from the bottom. So that's why this is an unshored concrete. Look, the lower portion is seen right here, and that's basically the difference. That show basically suggests that this is an unshored concrete. Clear? So look, this is how I say here there is no support to this beam, you see. So that's why this is unshored concrete. If we provide initially any kind of support like you see here in these slides basically, so then we can say this is, if we such kind of jigs or form work is provided to that beam basically, which you write here, see here, so then it is called a short concrete. So this is how we differentiate between these two concrete process. Clear? Now you must remember, you just read this theory. I already mentioned you that initially shoring is provided to a concrete for a 28 days, okay, that the concrete gain its 75 strength, and after that it's removed. Then we call that a shoring concrete. And if you don't provide it, then it is called unshored concrete. Clear? So all thing I explained, okay, I don't need to repeat them. Unshored, look, if you are doing an unshored concrete, means you are not providing formwork basically before concrete covers. No, once the concrete not covered up to 28 days, before you can say 28 days, the whole weight is taken by you can say by your beams. Okay, in this case basically you have to account for extra machinery loads, and that point is right here. Okay, you must remember, okay, this point you must remember. You see the different machinery which is called construction machinery, okay. You see all these men loads, these machinery loads which are constructed loads, and a 20 PSF is basically taken for these kind of loading in your design. Clear? So this is very important point which I want to show you, okay, here. And similarly, unshored after concrete covers. Now, before concrete covers, you have to account this extra load. Although you have to consider no live loads. Okay, the live loads which is basically considered in our design. In that process, you don't need to consider that live load. Although you have to consider dead load of beam, which is acting over the, because you see here, we have a construction load, we have a dead load of this concrete, we have a dead load of these slabs, of these corrugated sheets and steel, and the dead load, or you can say the self weight of the beam at this stage. Once this concrete is covered, and you can say 28 days, up to 28 days, after 28 days, so what will happen basically, the live load then come, okay, and then we design, basically we design before 28 days and after 28 days. So this, once we make analysis of composite section, we basically did analysis for both these two stages. Once after 28 days, before 28 days, and up to 28 days, you can say. Means when concrete not covered, means before 28 days, and when concrete covered, in concrete cover means after 28 days. So these, for we will design, and you see in the example, we will design for these two stages. Clear? So after composite behavior is achieved, so when you achieve your composite behavior with the concrete cover means up to 28 days, all loads subsequently applied will be supported by the composite beam. Look, this is the basic difference between these two. In unshored, before concrete cover means before 28 days, there will be no live load. Okay, in analysis you don't care about your live load. You have to consider what kind of loading. You have to consider the dead load or the self weight of the girder, the slab weight, as with the dead load of the slab and the construction loading. Clear? But after concrete covers, you don't consider your construction machinery weight, that is 20 psi. We ignore that load. But we have to consider the dead load of the beam, the dead load of the slab, and live load, okay, of the building. So that's basically the key difference between these two. Short construction, basically in short construction, the advantage of this short construction, we don't need to consider these machinery weights, I think so, these concrete slab loading, okay, before, you can say before 28 days, we don't take these loading. But after 28 days, once your shoring is removed, so then basically the whole loads will be taken into account. Clear? But not the construction load. Okay, construction load only we will consider in this stage. Clear? So let us do an example. Okay, this theory will be right, just clear to you. Okay, a W12 by 50. Okay, this is section acts compositely. Basically, now each words keep, you can say, some word. Remember, you see, we have this section, clear, acts compositely with a 4-inch thick concrete slab, mean that it is composite behavior is achieved. The effective slab width, that is your BE, shoring is not provided. This is important. Shoring is not provided means this is an unshored concrete. Okay, no form work is provided. And the applied bending movements are as follows. From the beam weight, you see, from the beam weight, that is from the self weight of the beam, this much movement coming. And from the slab weight, this much basically movement is acting. Now, and from the live load, this is this is basically the load which is almost be considered in the design process, that is the live load moment. Do not consider any additional construction loads in this example. That is the key point which you kept in mind, that 20 feet is basically the construction load. You don't need to consider that loading. You have this steel property of steel material, that Fy will be 50 kSi for the steel, and Fc prime is this one. Determine whether the flexural strength of this beam is adequate. Okay, assume full composite action. Okay, this point is very important. Okay, and assume that the formwork provides lateral support of the steel section before covering of the concrete. You know, this is important. What it means, that here they say shoring is not used, and here that the formwork provides lateral support of the steel section before covering of the concrete. This point is very important. You don't need to be confused with this one. Clear? Shoring is something different, but formwork is something different. Clear? If I show you in these slides, the difference is, you see, these vertical supports are basically shoring. These vertical supports are basically shoring. In this question, they basically says these vertical supports are not provided, but formwork is provided. This means they provide basically horizontal supports. Okay, here you can see these supports. Okay, but how they support these formwork? They support these formwork on the beams. Okay, they place those boards, or you can say on the beam, and that beam is basically support the load of that formwork. Okay, there is no external, or you can say extra vertical support, but beams are responsible for taking that load. Clear? Of the formwork. So at the initial stage, when the concrete is not covered, you can say, the beam are responsible to take its own weight, this formwork weight, as well as the slab weight, and as well as the construction weight. But the construction weight is zero because they say no construction loading will be considered. So let us start. Okay, here you see, compute the nominal strength of the composite section. The compressive force C is the smaller of A is Fy. Okay, the same thing which I did already. Okay, and C. You have to find out C, and you have to find out your tension. Now you have to choose this one because this one is smaller, so your C value is 730. Now this decide that your P in A will lies within the concrete because this one is smaller. Now you have to find out A, that is C divided by that term, 2.9 at 2 inches. Now the moment arm Y, and you know that Y is what? Now remember, you have a section of W 1250. You need to draw the diagram, okay, as we draw in previously. Okay, and here you see, I think so they do not draw the diagram. Okay, but as previously you see in that example, they draw a clear diagram, so you need to draw that diagram and you need to find out your Y value. Clear? So where we are, you find out Y, you need to find out your Y value. I did okay this formula. I use this formula basically in my lecture number 5, 6, I think so. So basically repeat that example number, question number 5. Okay, so you know about this, and you need to draw basically the diagram. Okay, then you will easily understand. Now you have to find out your nominal moment capacity, and it comes out to be basically that is 6 and that is 523 feet. Now you see, this is the moment basically, or the capacity before the concrete covers. There is only dead load, no construction load in this example. Now see, before the concrete covers means before 28 days. There is only dead load. Now that dead load, the dead load of the beam as well as dead load of the formwork, or you can say the slab. Hence load combination, you can see. Now this is very interesting. Okay, almost we use 1.2 of dead and 1.6 of live, but here this case will govern. Why? Because if we consider that case number 2, 1.2 dead, although we don't need to consider live load. Why? Because it is in initial stage, you say, and before 28 days there will be no dead load, because you see in this video, as there is construction starts, and there will be no one will be allowed. You don't any kind of work up to 28 days. When 28 days is completed, after that, you know, this floor will be in, you can say, will be in function. So after once the floor will be in function, then the live load comes. Okay, so here you don't need to consider, because in initial stage you don't need to consider that live load, but you have to consider the dead load. This 13 is basically the self weight movement of the beam, while 77, this is that movement basically which comes from the slab load, from work load. Clear? So that's why they consider these two dead loads, not live loads. Although if you multiply these two with a 1.2, so obviously it comes out lower value than 126. Clear? So that's why they basically select, or they use this combination, not the 1.2 and 1.6 combination. Clear? Now you need you find out your movement, that is 126 foot kept. Okay, now you have to find out the strength of this section. You have section that is W1250. You need to go to the manual and choose from your ZX table. Okay, from your ZX table, basically, as the section is, you find out, you go to the ZX table and search this section. Clear? Search this section and finally this is AIC LRFD manual. Okay, in LRFD manual you have to search out in chapter number 4, basically page number 19. So you need to memorize these things. Okay, where the ZX table, basically. Okay, so you come out to ZX table, you need to keep these values in mind, because we have this case, not this case. Clear? And now what we have to what we need to keep in mind, we have to find out basically this one. Clear? Now going down, basically, and you find out your strength. Okay, here we have W12 by 50 section. We have let me check. We have W12 by 50 section, and its strength will be not this one. Here, the W1250 have a strength of 270. Okay, you see here, this one, right? This one, clear? 272. And if you have the AISC manual, okay, that is basically 14th edition, then you need to search ZX table and Fy equals to 50 ksi, and this is your required strength. So you need to scroll down, and this is your 270. So 272 or 270 is your desired strength. So they use, I think so, 270. Clear? Because they uses that AIC manual. Okay. Now that is 270 foot convert. Okay, so that is more than basically 125. Remember, basically one important question is that why we are using this table. Okay, because this table is just only for a girder. Okay, not for a composite section. The answer is that because we are in the initial stage, we don't considering, because we are before the complete levels, means before 28 days, the concrete not gain its strength. So if it doesn't gain its strength, this means we cannot use the strength of concrete. So that's why basically we use that ZX table. Now after the concrete has covered, this is important. Now this is the stage after 28 days. We are talking right now after 28 days. Now after 28 days, this means concrete gain its strength. Now concrete gain its strength means now we can consider the composite action of both beam and concrete. So that's why we have to now again need to calculate the moment. Now the shoring, the formwork, all things will be removed. The beam and the slab is responsible to support its own weight and the line. So that is the reason that why we are using this MU. Okay, 1.2 and 1.6. Look, this is the clear difference. It shows that here we are basically taking 1.4. Okay, 1.4 times up. So this is basically stage 1. This is that case. Okay, this is that case. Now we are in this case, and in this case we have to consider no construction loading. We have to consider all dead loads of the beam and the slab as well as the live load. But in that case, no live load, only you have to consider the construction loading and basically the self weight of, you can say, if it is an unshored, so the self weight of the beam and as well as the slab. Clear? So now we are in the second stage, so that's why basically we are using this moment equation. We got 348, but here you see we use the ZX table, but here we will calculate the composite action, okay, right, which will act, and we already calculated that. In case of composite action, when you were both steel and concrete strength contributing, because when concrete gains strength after 28 days, in that case you see in this picture as well, both your concrete and your steel is contributing, and that makes the total strength of that section. Okay, so that is basically the total strength. So in that case we have a strength which we already calculated, and that strength is basically 523. So 523, you can say 24, is more than the loading, that is 348. So this loading is basically less than the required one, because already 424 is not factored, so that's why we factored it, and that is more than. So this shows that we are at the safe side. The beam has sufficient flexure strength. Okay, so this ends up, it will help you in basically in covering that question number 6 basically, which we have to do. Okay, although this major assignment is not finished right now, we have to use now the same concept here, and we did that example. So see you in next lecture. If you have any suggestion, any question, please share.